So I thought it would be maybe a good idea to do it in English. So maybe we can switch to French for the questions, but I'll stick to English for now. Thanks again for the invitation to talk about these models. So the talk is entitled Open Source Finite Element Models and Not Programs for Photonics with OneLab, GMesh, and GetDP. So all the models are bundled and in this simple web page that I will show you just after. Um, Oops. Okay, so here is the web page. On this page, it's very simple page. It's maybe just one screen long. It sums up all the models that we've proposed so far. So this collection, as we call it, of models is based on these three programs. So I will detail a little bit just after what they are. So they are all open source and the models themselves are open source. They are multi-platform in the sense that these three softwares work on Linux, Windows, Mac, and even Android. So you can perform simulations on your smartphone if needed. And it works from smartphone to laptops to supercomputers. And the philosophy that I've tried to stick to over the years is to have one paper that corresponds roughly to one model. So basically, when we write a paper, there is always, most of the time, one model that is somewhere on this page. So this framework is you can see each model as either some GUI model that you can use and click everywhere and just do not you don't even need to open the source code, or you can see it as a template model where you can just grab some elements that you would need for another application and use it as a collection of code snippets that you can copy paste all over the place. So that's how I use it. I use them all, as well. So a little disclaimer here because I'm really not the developer of all these wonderful softwares. They are all developed by Christophe Geuzen in University of Liège, electrical engineering department. You probably know Christophe for his wonderful mesher GMSH that has also a CAD engine, so you can build a 3D primitive very easily now. That was developed by Jean-François Remacle as well from UCL. GetDP is the companion that was the finite element software itself that is used to plug equation onto some mesh that is built by GMesh. That was developed by Christophe and Patrick. And OneLab is an interface to these two programs. And it was developed by Christophe and François Roth from Liège as well. So you see that really I'm not the developer of these softwares, but we've been reporting and adding features to GetDP for photonic applications. And the main one I would say is a lot of work has been done over the years on block boundary conditions, because in Fresnel we work a lot on diffraction gratings and photonic crystals. So this has to work very well, of course, and also on the support of high order edge element, which I will detail a bit after. And also we've been adding new features mainly to GetDP for analytical functions that we like to use in nanophotonics and photonics, which is vector spherical harmonics, for instance, green dyadics, and more. And also a big work that we've been doing lately is to have GetDP interface quite closely with SLEPSYS eigenvalue solvers for to compute quasi-normal modes, etc. So you will find, of course, the links to all these programs here. And now I'm going to focus on a little bit, first a little bit of history. So why this developing all these things? Well, for the anecdote, I was going to a postdoc back in 2009, and we quickly realized that it was not going to be possible as planned originally to install COMSOL on the supercomputer that I was working on. And so after the shock, then I decided to see if it was possible to do something about it using GetDP, because André Nicolet, who is a former researcher from Liège, told me it was maybe possible to do things that I was doing on console on GetDP, and so I tried it because the main features that it has to support high order elements to be quite accurate, to support block flow K boundary conditions, to have a nice interface to good direct solvers such as MUMS, Pardiso from MKL, Pastix from INRIA, etc. It's a quite high-level finite element library, so you can do really advanced stuff into it. It has backward compatibility, which is nice. You can develop the models that we've been developing for maybe 20 years are still working natively on the recent versions of GetDP. We can set up easily custom finite element formulations, as I will show later. And you can use it as just a matrix builder and then and just manipulate sparse matrices outside of these softwares. So the main contribution I would say that we have is on this webpage. It's a collection of models and not the programs by themselves. I will distinguish two types of problem in this talk. The direct problems when we have a source, like you have a scatterer and a plane wave incoming on some diffraction grating or an isolated scatterer. And eigenvalue problems where we want to find, let's say, band structures, optical modes, propagating onto some waveguide, or to do some modal analysis of dispersive structures. And I will also present after the everything that's in blue, and if I have some time, some recent stuff that we've been adding to all these things. So now, what is a one lab model? Well, a one lab model consists of three files. You have on the left hand side the mesher, Gmesh, that handles the geometry and the meshing parameters. And on the right hand side, you have this solver, getDP, which is who handles the dot profile, which when you incorporate your formulation, post-processing, etc. And above all, this one lab client that share parameters between those two programs. So you can share basically the main parameters as I will show in a quick example after. And when everything is run, you have your simulation results. OneLab also integrates and has the knowledge of what has been computed, and so it displays everything on the program. So just to give you a quick example, I will take a 2D model, and we want to be able to send on these two scatterers, the rectangle and the ellipse, either some near-field source on this point or a plane wave. We want to be, let's say, able to compute the scalar green function, or just to compute the scattered field when shining a plane wave in T and Tm. So how would it do that? I prepared a little demo on this. So you have these three files on the folder, and I'm just going to open Gmesh, open my dot profile. It's here in favorites. And I have, you see, this geometry that opens, and I just can hit run and have some simulation results right away. So you see on the left-hand side that there is no parameter involved at all. So that's where OneLab comes into play. Now if I modify a little bit the source code, we can go to the data file, that's the OneLab file. And you see here I define all the constants that are usually defined in a model. Constants, some flag, do I want a plane wave? Do I want what the wavelengths, what is the working wavelengths in harmonic regime? Many parameters. So if I just replace these declarations here by some OneLab syntax, introduced by define constant here, these variables will be available on the GUI of GMSH. And so I'm just going to do so for everything that I've prepared. Up. Now it's done. And I can just reopen my model here. And now, as you can see, I can switch from the left-hand side to switching the polarization case, T or TM, switching from a plane wave source from a source point, setting the free space wavelengths, um, changing the source of my source point, etc. And I can just rerun the model, and you see that the total field is now modified accordingly. So it's quite convenient if you, when we, for instance, collaborating with some colleagues, we can really give the model to some colleague with just a few parameters that they can modify, so that they don't have to dig into the model, because as you can see, the model itself then consists of a geofile, where I'm not going to comment it, it's just a geometry definition, and of the profile, which can be quite big, sorry, because we define all these getDP things, which are, I'm not going to do them all, but to bind all my domains to the Gmesh mesh. So it's just the definition of the domains. Then you can define many functions for the permittivity, the incident source field, etc. So it can get quite big. And so we can use these models just in a GUI mode. That's what I wanted to say. And now we are going back to the presentation. So now I'm going to present the models, but I wanted to do a little bit of a reminder on the scattered field formulation, because all the models that I'm presenting after are depending on this formulation. So let's say we have some source J here. This is the vector Helmholtz propagation equation in presence of a source J in harmonic regime, of course. And we are looking for the scattered field and the total field in this region where J is arbitrary. So the scattered field formulation is quite well known. You remove the scatterer. Now we have some source J, the same one that shines, radiates into the another domain, which is the problem called annex. That's why the epsilon R here is affibulated, let's say, with an A, like annex. And we have the solution. We know analytically, usually, or numerically, the solution of this annex problem. And then we can formulate the scattered field as the difference between the total field that we are looking for in this first problem and the annex field, which is known. And so, as you can see, the left-hand side is a propagator for the diffracted field, and the right-hand side is now a known source term that has sources, volume sources, into the object that was scattering. So it's quite general, and we have the model that I'm going to present now depend on this formalism in various contexts that can be a little bit more tricky than the one I presented regarding the radiation condition, for instance. But so the annex field can be set up in the context of a superposition of plane waves, for instance, for defining Gaussian beams. It can be the solution of a multi-layer problem, like presented here, which is very handy in diffraction gratings and in nanophotonics. It can be a vector spherical harmonics, that, like shown here. It can be also a green function, for instance. If you have the analytical green function, then you can, of course, set up this scattered field formulation as well. Or it can be a guided mode. In this case, the guided mode would be the solution of the mode propagating into the waveguide without any obstacle into the waveguide. So in this last case, this would be the annex field would be a numerical solution obtained from some other finite element 2D problem, like I will show you a little bit after. So usually now the property of the scattered field is that it is outgoing away from the sphere circumscribing the scattering object, and so we can safely bound the computational domain with perfectly matched layers, and all this in the models that we show on onelab.info/photonics, you will find all these PMLs implemented, which is sometimes not so easy. The Cartesian one is very easy to set up, the cylindrical one a bit less, and the spherical a bit less again. So now we can call the PMLized domain material properties some like with tilted quantities. So epsilon r tilde is epsilon r of the physical problem plus the permittivity corresponding to the PMLs. And finally, what I would like to show you is that it's quite easy to move from a mathematical formulation to a GetDP formulation because the mathematical formulation of the scattering problem now in variational formulation by usually multiplying by some test function that belongs to the functions of finite energy. So the L2 norm of the field is finite and so has its curl. And so this is the variational formulation that we want to plug into any finite element software. So how does it go into GetDP? Well, this is the GetDP formulation, so I'm not going to, of course, comment all the words, but let's see how it goes. For the first unknown, my unknown here goes into some name. It's called U. Usually I pick U for the unknown field. The space function that I'm going to span with my test function in the Galerkin formulation, and my unknown lives in this field, so it goes there. And then we have three main terms that are going to become, after discretization, three sparse matrices. So you see that this GetDP syntax is quite close to the original mathematical one. And moreover, if we examine each term, it becomes quite easy, even though sometimes they're not so obvious to write. It goes the same for all the terms in the equation. And so in the end, it's just a way to try to convince you that it's not so hard to actually to write some variational formulation into GetDP, because it's the spirit of GetDP to be closer to the mathematical formulation, mathematical discretization of a finite element problem than to physics itself. So that being said, a little bit about the elements that are used in GetDP, because at some point you want to really find a discrete basis that correspond to your continuous problem. So when we deal with scalar problems, like in TM formulation, we use Lagrange elements that are called BF nodes in GetDP, and we do a vector problem. We use the basis function defined on edges that are in GetDP web elements. So you can check in, it's quite complicated on these elements if you're not familiar to the jungle of finite element. You can find a nice overview of this in the paper by and website by Arnold. It's the finite element periodic table, or periodic table of finite elements, that repertoriates everything in a nice way. Sorry. And also in GenBook, it's pretty well detailed, all the families of elements that are used. But in our case, in nanophonics, we're going to use scalar problems or vector problems. And so at some point, we have to define some function space, which is either mapping H grad or H curl. And so, well, that's the point of publishing the models, right? It's that these things you can just copy paste them and take them for granted at some point in the model that we publish. So now a little bit of applications of all this for grading. So we have over the years developed quite extended, let's say, model for diffraction gratings, and there is even a doc that's at the time of when I started writing this, I was not sure how to publish this doc, so it's just an archive document for now. And it can be applied to the scalar case, conical vector case, or 3D case. And I'm just going to show you some more advanced application of all this for this model, creating 2D.pro. If we try running the model, then you see that it has quite maybe it's too complicated this one. It that's the tendency that we have when you develop a model. Maybe sometimes if you're like me, you want it to be able to do everything, which is a bit illusoire at some points. But anyway, if we just run the model, we have several application mode that you can define. We can change the scatter size. You can change pretty much everything, and again get the fill maps, the diffraction efficiencies, etc. So what I gave access to is the grading period, every material defined in all these layers. We can switch from one shape to another. We can also have directly yeah, we can change the materials, we can change the incidence. It can be T, TM, conical, etc., etc. So it's quite an elaborate model, and maybe it has become too elaborate, but it's up to debate. So what's nice about OneLab is you can also loop over parameters um, quite easily from the GUI mode. So if you just hit that button close to a parameter that you define, you can set up a loop over the parameter that you want. So in the end, in this model, there is one application mode where you can actually loop over the wavelengths to get the spectrum of this grating. And of course, it computes as well the Joule losses and given some material dispersion that is possible to plug actual material dispersion into the model. It's also available in conical mounting. So in this case, the wave vector is outside the screen, and so we need to have a formulation that's a bit more tricky because we need a continuous unknown for the normal components that's towards us, and for the in-plane components we need edge elements. So it's a mixed formulation that is available in this model, etc. We can handle anisotropy, and it works as well in 3D. So we have also added the possibility to have a skewed lattice. Let's see if this one works as well. Yes, it's coming. So this is the skewed lattice one, as you can see, and we can try to run the model as well. So the 3D model is more or less the same, while this one is a bit big. So yeah, it's going to take a while to run, so I'm just going to skip that. To move to some application that we have featured as well is the possibility to there is one application that I show here for silicon nanowire solar cells where we can directly have the field scattered by this periodic arrangement, for instance. And now, on the same spirit, there's this model scattering.pro that's more or less the same, except that we don't use Floquet block boundary conditions, but perfectly matched layers that are all over the place. And so it's quite handy when you have an isolated scatterer in some background and you want just to have, for instance, the far field scattered by when illuminated by some plane wave, for instance. So we can also compute the green tensor for the three. If you have a dipole now oriented dipole, tiny dipole in the vicinity of this object, we can easily compute the green tensor. And this model also handles the quasi-normal modes, so you can switch from the study type here in between all these application modes. And the one that has been used, I know, by some other colleague is the ability to compute the T matrix of some isolated scatterer. So the T matrix relates the spherical harmonics. So here is how it goes. So that's why we implemented this function into getDP. So we have now a native support of the vector spherical harmonics into getDP and of vector partial waves, which are the stationary NNM functions and outgoing and ingoing NNMs functions, as defined by my colleague Brian Stout, who happens to be my office neighbor. So in this paper, we will detail all the recurrence relations to compute all these functions that are now hard-coded into getDP. And so in the end, we can easily compute the T matrix, which consists in shining this object by a stationary harmonic and to expand the scattered field onto the basis of the outgoing vector spherical waves. So what's quite nice about this is that we just change the source by some stationary M or N stationary function. And so it's of course, we reuse the factorization everyone. So we just invert the matrix one basically. Maybe I can show you the example. Yes. So this would be the scattering trimatrix model in action. So we have here just a sphere. Maybe we can take something else as a sphere, like a cylinder, and then run the model. So if it's not too big, yes, it's just going to be a few seconds to invert this matrix, which is roughly 100 kilo degrees of freedom. So now it's solving using mumps on my laptop, which is now ventilating a lot. I hope it's not going to crash everything. And I think it's not using a lot of processors now. Well, that's why it's important to invert the matrix only once. So here you see on this model as well that we have set up a spherical perfectly matched layer, which is quite cool to have for this specific model. So here you see that now it's computing everything, and since we are inverting everything, the left and the matrix that at stake, we can just switch between the sources, and it's going to slowly, one by one, just reapply the invert matrix to the new source term and reuse the factorization, and slowly build the T matrix of a single scatterer. Voilà. So I know this model has been now embedded into this as part of this very big study, T-matrix representation of optical scattering response, that is being published this year by the Karsten group, Karsten Rockstuhl group in KIT, by a colleague from Bordeaux, and so it's also available in this framework. Now, a quick word about waveguide, but you get the spirit. So for waveguides, it's a bit different now. We need to compute, let's say we have a waveguide that is structured. So I'm coming from, let's say, the top. I want to send a mode on this geometry, and I have a bunch of scatterers, and then we have again the invariant output. We can apply the same scattered field formulation in this case. So first we compute the modes of the invariant structure. It's another finite element mode because we don't have the analytical formulation for this one. So we do this in getDP, obviously. We solve a 2D problem that's an eigenvalue problem. I'm going to talk about these problems after. Of the invariant waveguide. And so we get these modes that are quite easy to recognize. On let's say the fundamental modes would be for T and TM, these two guys, and then the mode number 2 and 4 are going to be these two, etc., etc. And then what's nice is that we can use the same scattered field formulation to and to have the right hand side, you see here, to be one of the modes. So in the end, we can compute the energy balance of this weird setup, and also to project the modes onto the modes of the background waveguide, which means that if we see here a cut of this setup, you see the mode that is almost unperturbed at the entrance here, and then it propagates into the waveguide and interacts with this object that are at the top. So this is some model that we've set up with my colleague Gilles Renversé. It's not available on the on the GitLab yet. It's on the Fresnel with GitLab. I will change it, but yes. So now I mentioned eigenvalue problems. Let me quickly show you how it goes into GetDP. So the mathematical formulation for this is that we will need to find now some omegas or propagation constant depending on your problem, and eigenfield that belongs to in general to we should look for complex eigenvalues most of the time, uh, well, except in band structures, but okay. And the field that belong to some functional space. And of course, we have some boundary condition on the field, which can be periodic or Dirichlet or perfectly matched layers in the case of QNM, etc. So in this case, we don't have any source term anymore. And the variational formulation goes like this. And of course, omega 2 over c squared in this case appears as an eigenvalue of this general eigenvalue problem. After discretization, curl curl becomes this A matrix, and field becomes this B matrix. And in GetDP, beware that lambda, the eigenvalue, refers to I omega. It's historical convention, so it's don't forget about this imaginary number I, of course. And yeah, so we have this generalized eigenvalue problem that we can set up in GetDP very easily. You recognize the same formulation as before. There's only two lines because we don't have any source, so there's only two matrices. In the resolution, we want to generate these two matrices separately, and so that's possible. And then we just call the eigensolve command, and it just gives you the eigenvalues. Of course, we specify a target in the complex plane because these matrices are very large and have many eigenvalues. And so we have put a lot of work into having a nice interface to SLEPC linear solvers and non-linear solvers, as I will show later. So this command actually natively calls the SLEPC solvers, which are the well, I will talk about this solver just after. So now we are also able to solve non-linear eigenvalued problems in GetDP. So in photonics, in nanophotonics, the non-linearity occurs because most of the time because we have dispersive materials, and the dispersion is most of the time into epsilon, the permittivity. Mu is considered non-dispersive in this case because we want to take care of materials like gold, silicon, etc., which are amagnetic, so mu is 1. So let's say you have a domain that's dispersive and a background that's non-dispersive. It can be consisting of different materials, but they're all non-dispersive. How does it go? So now we can split this. It's simply we separate the non-dispersive part and dispersive part. So in the end, we get 3 matrices now that are driven by different you see functions of omega. This one is simple. Here is 1, and this one is some rational function that you want for your model epsilon or 2. So it can be, for instance, a rational function that, of course, incorporates the case of Drude model, Drude-Lorentz model, etc., etc. Usually, epsilon r is a rational function of omega. And so if you remultiply by the denominator of this rational function, you see that now d is a polynomial in omega, this guy is a polynomial in omega, and this guy is also a polynomial in omega. So getDP now is able to, so this kind of problems, sorry, are called polynomial eigenvalue problem, where you have some power of the eigenvalue times some matrix times the eigenvector that is equal to 0. So now we can, in getDP, have polynomial eigenvalue problem where we can switch, have different orders for the polynomials, up to 6 actually. And the syntax is pretty much the same as before. Recently, we've also added the rational case, which is to say that we can stick to this formulation. It's even more powerful, let's say. And a rational eigenvalue problem is defined by this kind of problem. So you have a rational function that is driving some sparse matrix that is the eigenvector again. And so in getDP now it has been interfaced. It's been a quite nice collaboration with José Roman, who is the SLEPC developer. He works in the University of Valence in Spain, Valencia. And so we have worked quite a lot with José to provide a nice interface between getDP and SLEPC. So you recognize now the three finite element matrices, the curl 1 and 2 field 1, let's say. And you see that we, in fact, in general, have three rational functions in front of this term. And let's see how it goes. So this is the three matrices that are built by getDP. And then we can just specify the rational functions to the eigensolver if we have a permittivity that writes this way. And so it's quite easy to actually just plug in a few lines of code, a rational eigenvalue problem into getDP. So there is an example of this that is the result of a collaboration that we've made with Laboratoire Charles Fabry and LP2N in Bordeaux with Philippe Lalanne, with a nice numerical ANR that we had, that Philippe Lalanne had a few years ago. And so if you open this model, for instance, it's the philosophy when we do a very numerical paper, we provide a model, and then if you just run the model, usually you end up with the one eigenvalue that is featured in the paper. So it just retrieves one very specific result of the paper. That's how it goes. So yeah, I'm not going to spend too much time on this. And also we are able to reconstruct a solution when you have to use these quasi-normal modes as a quasi-basis to reconstruct a scattering problem, but it's quite involved, so I'm going to skip that for now. And move to another subject, which is topology optimization that we have been working on with Simon Hans in PhD between the Lab of Astronomy here in Marseille in Institut Fresnel. And the question that was asked by a colleague in astronomy is that can we do better than a classical Blaze grating with some flat design, let's say a Mété surface. So this topology optimization framework that I'm going to present right now is very step by step. It's very much less automized than what Benjamin Vial presented in his very nice webinar a few months ago. Benjamin is using automatic differentiation, and here it's not the case. Let's say you have some grating. We model it with grating2d.pro, of course, and we set up some topology optimization domain. So it's a very usual setting, and the design region is here, Omega Design. Okay, and I can shine on this any plane wave because we're in conical mounting, which means that the wave vector can be outside of the plane of incidence. And the goal here is to fill by some material by any fraction between 0 and 1 of the material. So 0 being air, let's say, and 1 being glass. So Simon did this nice job to actually define, of course, the diffraction order, which is the classical formula in conical mounting. And the very difficult task was, of course, to compute the gradients because we need to know the gradients for topology optimization, which means to know the derivative of the reflection efficiency in any order with respect to one design variable, and one design variable being one mesh element. It, of course, would take a lot of time to do it by finite differences, for instance. And the difficulty, of course, is when you derive this, differentiate this diffraction efficiency with respect to the design variable, is that these kind of terms emerge where this little dr by d rho involves the derivative of the scattered field by one design variable, which is, of course, very difficult to apprehend, and we don't know this guy. So we use an adjoint problem, which is handled by getDP, and it's also what Benjamin presented. It's a very classical, except here we have to be careful. We're in conical, so the adjoint problem has some a lot of subtleties, let's say, with block boundary conditions and also by with the invariant direction, etc. But in the end, we find that the topology derivatives are given by some interference term between the total field of this left-hand side problem and the adjoint problem. So we get in very few finite element runs these derivatives that are quite involved to obtain in another manner. So the example that Simon has uploaded and is available in diffraction grating stop-up is to start from an initial already blazed configuration. So this is one period of the grating. We shine some light on it. If we do a single row optimization on a particular order, we obtain this blurred design. If we smooth it, we obtain a little bit let's say, round shapes. If we only binarize it, we obtain very, very small details. And if we smooth it and binarize it, we obtain this readable shape where dark blue is glass and very light blue, whitish is air. And in the end, this is the optimization history, and this is the spectrum. So the configuration was already blazed, but at the target wavelength, we obtain an enhancement from 81 to 98%, which shows that it works quite well. So you can see all the details in this doc. And Simon has also made a quite nice README file on this one, which details all the parameters in the model, etc. And of course, the companion paper is important to read to get all the details. In the end, we obtain a scattered field that is really, you see, we shine some plane wave with some incidence, and the -1 order goes back in the same direction, and it's almost unperturbed because it's one single period, one single plane waves that that makes the scattered field. Voilà. Ah, I have a little bit about chirality, but maybe it's good to keep a bit of time for discussion. So let's keep chirality. If you want to know more about the way we can take into account this constitutive relation, you can ask me ask the question maybe. And now let's talk a little bit about domain decomposition. It's been ongoing work for quite a while. It's been my confinement project. Um, so here is the situation. When you use a direct solver in console or in getDP or whatever, it's the same solver anyway. It's mumps. It blows at some points independently of the machine. I don't even remember the machine, to be honest. But to give you on the machine that I was working on at the time, this is 10 millions of unknowns, and you see that after maybe 7 millions of unknown, independently of my finite element order scheme, mumps just crashes and it complains I don't have enough RAM memory. So the way to uh, so these solvers are very greedy, and the problem is that they need one single piece of RAM memory to work, so they cannot be really parallelized. So there is this very nice method which is called domain decomposition method. It's actually a big family of methods that are very popular in the finite element community. Is to split the very large domain into small pieces, to do some direct solve on each small pieces, and then to reconstruct the global solution with an interface problem that uses transmission conditions. So let's say we have a meta surface here consisting of these scatters. What I did is actually to adapt the very nice framework which is called getDDM. Here in the ref, I show the reference to the paper by Bertrand Thierry, Christophe Gussen, etc. But here it's very adapted to meta surfaces, so it means that it was not so easy to move to this example using waveguides to a full setup with perfectly matched layers, substrate, etc. And to see if it still works. So the partitioning is doing geometrically. Mesh partitioning doesn't work currently. So it's very well adapted, I think, to these meta surfaces because we can split the domain into small pieces very easily. Each cubic domain, parallelepipedic domain here communicates with the neighbors with proper transmission condition. And in the end, you can see that when reconstructing the solution, the Gmesh residue goes down as very, very sanely. And the difference, the L2, the L infinity norm, yes, okay. The difference between the full model and the DDM model is tending to zero when you decrease the GMS tolerance of the solver when reconstructing the solution, and the absorption in the rod is very very good between the full model and the DDM model. So this is the map of the error, and the max you see a value of the map of the error is more or less the GMS residue tolerance. So it works quite well, and it allows to do a very very big runs in a relatively modest machine. I mean, the solvers are already available in commercial softwares. It's just that I'm working on a model to advertise this on OneLab. And finally, I would like to conclude by saying that these open source models um, are quite handy and can be used on laptops, workstations, large clusters. So we use them on various machines in the lab, and also it's been deployed in the classroom for teaching because I also teach, and it's quite nice to be able to do simple finite elements things with the students. Usually we start after maybe in licence 3, and of course in master we use them a lot. And well, if you want to model things with one large image KDP, maybe a good set of advice would be to start from a simple example, to have some analytical validation case, to run convergence tests. Energy-related ones are really are good choices usually. And then complexify the model to build up from existing bricks to just pick up some parts of the code that are available online. And of course, you can ask questions because all the models are on GitLab, on the GitLab of one lab, and it's not very used, I would say, now, the question part of question section of these models. But of course, you can ask questions, and if you ask a question on GitLab, I should receive an email on my Fresnel box, so I will receive it. Okay, that's it for me. I will thank you for your attention, and of course, I'm ready for questions.